Okay, so we're going to move on, show you some more examples on how to use equilibrium in acids. So here's an example of a problem. What's a zero point 0.1 molar weak acid has a pH of 4.25? What is the Ka for the acid? And I know I've kind of tried to get you to think this way quite a bit with an ice chart. So if it's zero point 0.1 molar and this is 0, 0, we shift right. So minus x plus x plus x, you have zero point 0.1 minus x, x, and x. And you have, so then the Ka is going to be H plus or H, not adding, you have to multiply it, hydrogen ion, anion all over acid, which is going to be x squared over zero point 0.1 minus x. And now you're like, well, what does x equal? You're given that with the pH. X equals, in this case, this is the hydrogen ion concentration. This is also equal to 10 to the minus pH equals 10 to the minus 4.25. And then plug that back in for x, and you get your Ka equals, you throw that back in there and find the x, and you get 3.1 times 10 to the minus 8. So one way about this, though, don't just get kind of stuck in on doing a problem the same way each and every time. You have to be able to think outside the box sometimes. So this is an example of one where, yes, you're already in the ice chart, but you can use that then to your advantage. Well, in this case, recognizing that X is your extended reaction here is your hydrogen ion concentration, and then working back that ways. Okay, and I mentioned before, weak acids uh, tend to stick together. And here's an example of one. And here's nitrous acid, and find the percent ionization. So this is also considered common sense. The percent ionization is how much you break apart of your original amount times 100%. That's your percent ionization. And that's not really an equation given, but it's considered common sense. So one other thing with you as the student doing this, you do have to is assume that you're going to have some chemistry common sense. But let's go ahead and start this. So nitrous acid, so 2.5 molar, 0, 0, shift right, minus x, plus x, 2.5 minus x, x, and x. Our Ka is equal to hydrogen ion nitrite over nitrous acid, so 4.6 times 10 to the minus 4 equals x squared all over 2.5 minus x. Apply the x is small approximation, x squared over 2.5, and that means x equals the square root of 2.5 times 4.6 times 10 to the minus 4, which is x equals 0.034. So if it ionizes 0.034, starts off at 2.5, so your percent ionization is 0.034 all over 2.5 times 100%. And looking at it, this is 1.4%. So recap with this one. So we have nitrous acid, initial change equilibrium, start off with 2.5 molar, and figure out the ice chart with the extent of reaction shifting to the right. So minus x the reactants, plus x for the products. Write the equilibrium expression, put in the numbers, apply the x equals small approximation, get x is 0.034, and then compare that to the original. So 0.034 breaks apart, and it's originally 2.5 molar, so it only ionizes 1.4%. So that means that this is a bit of a stronger weak acid. The Ka is pretty big compared to other weak acids, but still, it mostly stays together. It's not very strongly molecular. Okay, so what about if we have a strong acid and a weak acid together? So in this case, so we have a mixture that's zero point 0.1 molar hydrochloric acid and zero point 0.1 molar in formic acid. So this is something known as the common ion effect. So, meaning that when you write the initial change equilibrium for this, that you include the 0.1 from the hydrochloric acid. So you have this case, and then you initial change equilibrium. So just like I put in the textbook, you have to include that in your calculation, and then include the value when you set up the equilibrium expression. If you solve for x here, it turns out x is 0.00018. So when you go back, so your x is 0.00018. So when you go back to write out the expression for hydrogen ion, you have to include that in anything with a pH. Oh, I guess I'm missing one too many zeros, sorry. 0018. So remember this, and this will come in more important next chapter. We talk about the common ion effect, but if you have mixtures of acids, this is known as the common ion effect. That's also when we talk about sulfuric acid and other diprotic acids. We'll cover that in the next video. Okay, so I mentioned strong bases. So just like strong acids, we have strong bases. And you might notice some things: lithium, sodium, potassium. I could also say rubidium, cesium. Those are the alkalis. And look, there's the alkaline earths as well. So those are the strong bases. And if you notice the first two columns of the periodic table, you can compare that. You got that's something easy to remember, right? You have the strong acids there: HCl, HBr, HI, nitric, sulfuric, perchloric. And then you have just really the two rows of the periodic table for the strong bases. So it's going to be easier to remember the strong bases. So here's some weak bases. So everything else is a weak base. So conjugate bases like the carbonate anion. And notice the word amine. Amine have nitrogens in it. So once you hear the word amine, so amine is it's a nitrogen-containing compound that has an organic compound that has nitrogen in it. So organic means carbon-containing. So methylamine, and I can tell you the thing about amines, they all smell terribly. Ugh. So chemistry, unless you're working with perfumes, chemistry is kind of a stinky job. So if you're working with amines, you're gonna have some nasty smelling stuff. Even ammonia has a pretty strong smell, of course. But there's other things like cadaverine. That's the stuff that cadavers release. And you might other things like amphetamine. We already talked about vitamins, or used to be vital amines. But okay, so but amines, these are all bases. So, and many of them are also known as something called alkaloids. Those are plant basic compounds, and those are almost all amines. So like the nitrogen bases for like in the DNA molecule, those are all amines. And a lot of other alkaloids, the alkaline plant things, so things like nicotine, that's an amine, but there are many weak bases. Okay, so let's do some calculations. We switched from acid to base. What is the hydroxide ion concentration and pH of each of these solutions? So we have there here we have 0.2 0.225 molar potassium hydroxide. So hydroxide concentration is 0.225. I'd probably use the pH as like so. So pH plus the POH is 14, or pH is equal to the or 14 minus the POH. I prefer to do it this way. You can also use the equilibrium method by the fact that Kw is the hydroxide times the hydrogen ion concentration. I don't like doing it that way. I like doing it this way better. So this is 14 minus a minus log of 0.225. And if you put that in your calculator, you get 13.35. And there should be one more sig fig there. So, all right. I'm looking at the textbook. There should be one more sig fig that have 3 sig figs. I'll just put a 0 at the end of it. And then for the next part, B, so this is 0.0015 molar strontium hydroxide. So because there's a 2 here, the hydroxide ion concentration is double that. So same thing, pH is 14 minus a minus POH equals 14 minus a minus log of 0.003, and put that in your calculator. You get 11.48, and that's the answer there. So that's how you solve hydroxides and finding pH using hydroxide ion concentration. And now let's do one involving a weak base. So what is the pH of a 0.1 molar ammonia solution? So now I've written out ammonia plus water, equilibrium with ammonium plus hydroxide. So this type of reaction, this is known as a hydrolysis reaction. And this is also considered to be chemistry common sense. So you, the student, needs to know and understand how the different bases are going to, acids and bases, you have to know how they're going to react with water. So that's considered a hydrolysis reaction. So you, the student, are in charge of knowing that. And again, that's considered chemistry common sense. So if you're going to if you're a STEM major and you're taking this class, you have to understand that is considered, like I said, common sense. So understand that. If you have a hard time understanding this, review this, and or write me or come and see me and we can talk some more. Okay, but how do we do this? The pH of this solution and it's 0.1. So initially this is 0.1. Water is solvent, it's not included. 0, 0. We shift right, so this is minus x plus x plus x, 0.1 minus x, x, and x. And the Kb, this is going to be the products, NH4 plus hydroxide all over ammonia, like so. Well, why don't we include the water? Water is a solvent, so this is all aqueous, and you do not include the liquids in equilibrium constants, if you recall. So then this is 1.76 times 10 to the minus 5 equals x squared over 0.1 minus x. And apply the x as small approximation. X squared is equal over 0.1. That means x squared is 1.76 times 10 to the minus 6, right? You apply both sides by minus 1. And then x is just a square root of 1.76 times 10 to the minus 6. And what is that? So that is equal to 1.33 times 10 to the minus 3. And among other things, this is, oh, I just moved this back. Sorry, I forgot the equal sign. Equal sign there. This also equals the hydroxide ion concentration because that's what the x is. So you have 14 minus a minus log of 1.33 times 10 to the minus 3, as we've done in the last example. And this is 11.124 is our pH. So we just did the last example to show you how to calculate pH from hydroxide ion concentration, and this is how you use the for the weak base. So remember what each term is solving for. So in a weak base, you're going to be solving for the hydroxide ion concentration, and when you write it with the hydrolysis reaction, so then when you figure out the pH, you have to use that for those calculations. Okay, and the last thing in this short video, comparing Ka and Kb. So next thing I'll do is we're going to talk about when we have different conjugate bases. So the acid. So if you have an acid times its conjugate base, the combination of the acid times the Kb of its conjugate base equals Kw. And the same thing for a base with its conjugate acid. The multiplication of those two constants is the Kw. So keep that in mind, and we'll talk about that in the next video. But generally speaking, the stronger the acid, the weaker the conjugate base. So so there's an inverse proportion with that. And the other thing, cations can also be weak acids. They're conjugate acids, but in general, they are also weak acids. So, but like I said before, they are conjugate bases from that. But okay, so moving on, we got one more section to go in this chapter.